In 1956, nuclear physics was in genuine crisis. Beta decay, one of the most fundamental processes in all of atomic science, simply refused to make consistent sense. The theories were contradictory, the mathematics was breaking down, and physicists across the globe were stumped. That is, until Richard Feynman stepped in. Beta decay is one of nature's most basic radioactive processes. Inside an unstable nucleus, a neutron transforms into a proton, releasing an electron, what we call a beta particle, along with an antineutrino. It's governed by the weak nuclear force, one of the four fundamental forces of nature. Simple enough to describe, but devilishly complicated to model mathematically. Enrico Fermi laid the theoretical groundwork back in 1934 with his landmark theory of beta decay. He modeled the interaction after electromagnetism, using what physicists call a vector current. Fermi's theory worked beautifully for low-energy decays, but it started showing serious cracks as experiments became more precise through the 1940s and 50s. By the mid-1950s, physicists were wrestling with a deeply unsettling problem. A particle called the Kaon appeared to decay in two different ways, each producing different parities. The mathematics began to suggest something truly disturbing, that parity, a fundamental symmetry of nature, might be violated by the weak nuclear force. Parity is the principle that the laws of physics look identical whether you observe them directly or in a perfect mirror image. In 1956, Tsundao Li and Chen-Ning Yang published a groundbreaking paper making a radical, almost heretical proposal. The weak nuclear force might actually violate this sacred parity symmetry. Most physicists refused to believe nature could be so asymmetric. Then came Qin-Shiung Wu. In early 1957, Wu cooled cobalt-60 nuclei to near absolute zero, aligned their spins with a magnetic field, and carefully measured the direction of the electrons emitted during beta decay. The experimental result was utterly unambiguous. The electrons had a strong preference for one direction. The mirror symmetry of the weak force was shattered beyond doubt. This experimental result broke the existing theoretical landscape wide open. Old models had used various combinations of interaction types, some vector, some axial vector, some scalar, some tensor, and none of them could consistently explain the full body of experimental data. Nuclear physics was, in a very real scientific sense, broken. Richard Feynman and Murray Gell-Mann decided to approach the problem from a completely different angle. Rather than patching up the existing theories with correction terms and ad hoc additions, they asked a deeper question. What mathematical structure would nature actually prefer? They followed the mathematics wherever it honestly led them. Their answer became known as V-A vector minus axial vector theory. They proposed that the weak nuclear force couples to one specific linear combination of two types of currents, the vector current and the axial vector current, with a very particular minus sign between them. The vector current, labeled V, transforms in a standard way under the Lorentz transformations of special relativity, just as the electromagnetic current does. Under a parity transformation, the vector current remains unchanged. It is what physicists call parity even. The axial vector current, labeled A, behaves differently. Under a parity transformation, it picks up an extra minus sign compared to a regular vector. This sign difference is precisely what encodes the asymmetry, the inherent handedness, of the weak nuclear interaction. By forming V-A, Feynman and Gell-Mann constructed a weak current that is maximally parity violating. This was not a fudge factor or an ad hoc correction. It was a clean, mathematically precise statement about the deep structure of nature at the subatomic level. The mathematical heart of V-A theory lives in the interaction Lagrangian. The weak interaction term is written as Gf over the square root of 2, multiplied by two currents, each taking the form psi bar gamma mu times the quantity 1 minus gamma 5 times psi. That factor, 1 minus gamma 5, is the defining mathematical signature of V-A theory. This factor, 1 minus gamma 5 acts as what physicists call a chirality projector. It mathematically selects only the left-handed chiral component of any fermion field and completely discards the right-handed component. The physical consequence is profound. The weak nuclear force only interacts with left-handed particles and right-handed antiparticles. It entirely ignores right-handed matter. This had an extraordinary experimental prediction baked directly into the theory. Neutrinos must be purely left-handed particles. They carry absolutely no right-handed component for the weak force to interact with. In 1958, Morris Goldhaber and his colleagues measured the helicity of neutrinos directly and confirmed the prediction. Neutrinos are left-handed. Every single one without exception. Feynman and Gell-Mann also demonstrated that this V-A structure is universal across all weak interactions. The same coupling constant Gf, which we call Fermi's constant, appears identically in muon decay, in electron capture, and in every other weak interaction process. The weak force is governed by a single, unified mathematical law. Experiment after experiment lined up in support of V-A theory. Polarization measurements, neutrino scattering cross-sections, decay angular distributions. The predictions matched the data across the full range of observed phenomena. V-A theory wasn't just a reasonable model, it was the correct one. V-A theory became the essential theoretical stepping stone to the full Electroweak unification developed by Sheldon Glashow, Steven Weinberg, and Abdus Salam through the 1960s and 70s. Work that earned them the Nobel Prize in Physics in 1979 and permanently reshaped our understanding of the fundamental forces. In the Standard Model, the W boson mediates the weak nuclear force, and its coupling is built directly and mathematically upon left-handed currents. The V-A structure is not a historical footnote. It is literally embedded at the deepest level of the gauge theory that describes the weak interaction in our most successful theory of particle physics. What made Feynman's contribution here truly extraordinary was his willingness to follow mathematical elegance even when it conflicted with established physical intuition. He and Gell-Mann were willing to be wrong, but they trusted deeply that nature at its most fundamental level would be beautiful and internally consistent. V-A theory transformed nuclear and particle physics from a contradictory, fragmented collection of incomplete models into a unified mathematical framework. It stands as one of the most important theoretical physics breakthroughs of the entire 20th century, and Feynman's direct role in it deserves far greater recognition than it commonly receives. Here is something genuinely extraordinary to sit with. Every single time a radioactive nucleus undergoes beta decay anywhere in our universe, at any moment, the emitted electron is left-handed. Not sometimes. Not usually. Always. That universal asymmetric truth, written into the very fabric of physical reality, was first revealed and mathematically articulated through Feynman's V-A theory. Feynman did not merely repair a broken theory. He uncovered a fundamental truth about the chiral, asymmetric nature of the weak nuclear force. He showed us that our universe has a preferred handedness at its most elementary level, and that extraordinary discovery changed the course of physics forever. If this video helped you understand V-A theory and Feynman's remarkable contribution to nuclear and particle physics, give it a like and subscribe to the channel for more in-depth educational physics content just like this. Drop your questions, your thoughts, or your challenges down in the comments below. We read every single one and genuinely love hearing from curious minds.